Hello everyone, my name is Aisha Akil. I'm from Lahore, basically from Lahore, Pakistan, and recently in my visit to Pakistan on holidays, I have given a talk at two different universities from Lahore. One is LUMS and one is FC College University. And I here would like to record for just information this talk. So I would like to share. The topic was novel magnetic materials which can host fermions and can be useful for spintronics. As I am affiliated with Technical University of Munich, and I would like to share here a little bit about Munich. I am working in the area of Bavaria, and the capital is Munich. One very famous affiliation with Bavaria is Bayerisch Motor Works, which is BMW car, very famous everywhere. So this is actually from this area. One important thing about Munich is it has a lot of industries as well as universities. Many of them are people know a lot. One of them is Technical University of Munich, Ludwig Maximilian University of Munich, which is called LMU, Walter Meissner Institute, and Max Planck Institute for quantum information. So, as there are a lot of universities, there is also its own quantum valley, which is known as Munich Quantum Valley. So, a lot of investment from the German Physical Society for quantum information and technology applications. And one cluster of excellence is MCQST, which is Munich Center of Quantum Science and Technology. So here I would like to first thank um, the authors which have helped me a lot in the work which I'm going to present. Firstly, Maxime Mostovoy from University of Groningen, Netherlands, and Maria Azhar from University of Karlsruhe, and all other authors, Christian Bach, our group leader, my group fellows, and as well as I would like to thank MCQSD, this cluster of excellence in which I have funding to host a mini group. And I work in the big group, Functional Spin Systems with Christian Bach. Before going further, I would like to tell you what you are going to expect. So I'm going to talk about chiral magnets, in which I want to discuss pinhole magnetoresistance. It's mainly a very experimental talk. I will talk a little bit about calculations which we did to agree with the data. Luckily, I don't have to tell too much about chiral magnets. You know, crystals are symmetric. There are a lot of symmetries involved. They are periodic arrangements of atoms. One symmetry which is very important here is inversion symmetry. So materials where you apply inversion operation, you take a position of an atom which is x, y, z and change it to minus x, minus y, minus z. It will remain the same, just like a circle or a square. So it's a periodic arrangement, but very centrosymmetric. However, if you look your hands, this won't be the case if you move one finger to another. So our hands are very non-centrosymmetric or very chiral. We have either left hand or a right hand. So if you apply inversion, left hand doesn't stay left hand. It will just go into the right hand. So the point what I wanted to make here is that in reality, there are not only our hands, but there are also some crystals like DNA and other organic molecules, or even single crystals in which atoms are distributed in such a way that they are either left-handed or right-handed. And if you apply inversion, they will not stay the same. Okay, here is an example, manganese silicide, where manganese is magnetic in this material, and the position of this is in such a way that if you um, try to rearrange it, it will not stay the same. So you will have either literally a left-handed crystal or a right-handed crystal. So far, so good. So we have discussed that there are systems which are just like our hands crystallographically. So what else? So important thing is that this is not only about crystal. Their crystal properties influence drastically their magnetic properties. So there is another interaction, Jeloshinsky-Moria interaction, which actually plays a role if the system has such uh, an inversion symmetry broken. So here you can see that neighboring spin Si and Sj are represented with a cross product. You know about exchange interactions. They are the interactions with which you align spins parallel to each other, and the Hamiltonian is with a dot product. So meaning the exchange interaction align these spins parallel to each other. An example is shown here. But in the Jeloshinsky-Moria interaction is a cross product. So meaning it tries to align spins perpendicular to each other. And this is usually it will not fully align perpendicular to each other, but it will twist this structure. So here you have fully ferromagnetic example where everything aligned parallel, and here is a twisted structure. So if you have a chiral system, you can have a non-zero Jeloshinsky-Moria interaction because it is an interaction which depends on spin orbit coupling, as well as it is anisotropic and antisymmetric, means the invariant symmetry must be broken. And then you can have some twists. Okay, so let's see an example. The systems which I'm talking about, they share a generic phase diagram. Usually, if you talk about magnets, you don't see such diagram. Usually, at higher temperatures, above Curie temperature is only paramagnetic, and below Curie temperature is only ferromagnetic or antiferromagnetic. Meaning that if we talk about ferromagnets, everything will be aligned along the field direction below the Curie temperature. But here you can see a color, different colors changing as function of field. And the phase diagram is defined in a way that at your y-axis there is field, at x-axis there is temperature, and one represents Curie temperature. And here the colors represents that there are some changes in the magnetic order. So if we look here, the difference between this state paramagnetic and field polarized, they are just as you expect in normal ferromagnets. So above Curie temperature it's paramagnetic, below Curie temperature is ferromagnetic or field polarized, meaning everything is aligned with applied field. What's interesting is as function of field, as you go down, you can see that at lower field, these neighboring spins will start to twist, making a spiral type configuration. And as you lower down the field, the angle between the spins will increase with respect to applied field. And in helical state, it's almost 90-degree, and it's also a multi-domain state. Conical is a single domain state. But one interesting thing which really increased the interest of different research groups is this fermion lattice. So in a small pocket here, you get some very strange twist just in circular fashion, and these circular rotation of the moments make a topologically protected skyrmion, meaning that you need to apply certain energy to destroy them or to go from skyrmion state to a field polarized state and back and forth. So They are topologically protected. So topology is actually mathematical concept. Before going further, I would like to just mention that they are very complicated. You have to extend them in third dimension, and they make some rods. We are at the moment, the focus is that you have different twists with different angles, and they are different from your normal ferromagnets where you do not have such twists. So you have very rich phase diagram. One important thing here is that this phase diagram which I share is only for very bulk systems. As you thin them down, the phase diagram changes quite a lot. Uh, the B20 compounds, they are B20 compounds where a lot of them share this generic phase diagram. But one important thing is that these are all metals or bad metals, but only one material, which is copper oxyselenate, is very good magnetic, very good electrical insulator. So it's a magnet, but electrically it's an insulator, meaning you cannot pass the current through it. So we are actually interested in materials which have such interesting phase diagram, but they should not pass electricity. So electrically they should be insulators. Then you will expect to have less scattering events, and electron scatterings are uh, not dominated there, and you will have a very you expect to have very low magnetic damping if your material is very pure. From crystal point of view, we can grow these copper oxyselenate type crystals very large, and up to size of around 1 centimeter, with very high purity, with both chiralities and with very low magnetic damping and no measurable twinning. So meaning they are really, really pure, and further information can be followed here. And their purity was also very visible in these experiments. Now I showed you a little bit about the system which we wanted to discuss, but now the point is that it's an electrical insulator. I want to introduce a technique where we can um, uh, uh, measure it by electrical means, the magnetization of this material. The method is known as spin Hall magnetoresistance. So to do spin Hall magnetoresistance, we want to detect this phase diagram of a material where you cannot send current. So we want to put a metal on top, and by measuring the resistance of this metal, we want to understand whether there is a helix or the conical state, or there is a field polarized state. What we do, we grow such crystals, we polish them, make them flat, and on a certain crystal direction, we put a hall bar type structure. Here is platinum, here are gold contacts. And this structure is done with e-beam lithography, but in reality, you do not need any sophisticated technique. You can also use shadow mask, or you can use UV lithography, so on and so forth. So to understand spin Hall magnetoresistance, first we have to understand spin Hall effect, because in spin Hall magnetoresistance, spin Hall effect and its inverse spin Hall effect plays an important role. I will only talk about spin Hall effect. So compared to your ordinary Hall effect, where you have to apply magnetic field, you get a Hall voltage, but there is no spin accumulation. You only get a Hall voltage because of the Lorentz force on the electron when you apply a field perpendicular to it. However, in this spin Hall effect, we are talking about pure spin currents, meaning there is no Hall voltage, because you can see one electron is here, charge, and one equal charge is here. So there is no Hall voltage, but there is a spin accumulated. If we look a little bit more to it, for this effect, you do not need any magnetic field to be applied. What happens if you have a heavy metal, we are talking about platinum, tantalum, and very heavy metals with very large spin orbit coupling. You send a charge current. Now, here it's a normal metal, and M means a normal metal, meaning there is no, it's not magnetic metal. So there is no unequal spin up and spin down electron. Equal number of spin up and spin down electrons are there. Here, the defined direction of spin, I will still call it one spin up and the other one spin down, although I have defined the spins within the plane, but doesn't matter. Um, the point here is that we can define this charge current as a sum of spin current associated with spin up and spin down charge current densities. And as it's a normal metal, you have equal number of spin up and spin down going in same direction, meaning you have only charge flowing in this direction. There is no spin really flowing in this direction. However, if you look the arrows in the transverse direction, where what happens if you are sending a charge current through a heavy metal due to spin orbit coupling? Spin up electron get an opposite sign than the spin down and they deflect in the opposite directions. And you can define a spin current, which will be difference of the spin up charge current density and the spin down charge current density. One important thing here is that it's literally a flow of angular momentum. That's why usually we write this h bar over 2 with the 1 over e term just to show that it's literally a flow of angular momentum. So you can define a spin current. You can see here that for spin up and spin down, you will get opposite sign. So you have a total spin current moving in one direction. If you have a normal metal like platinum or other metal, you cannot really measure this spin current because there is a backflow of spin current in the opposite direction. But the point what I wanted to make here is if you have a heavy metal, you have some spin accumulation at the edges. This is a non-equilibrium process, meaning you have to send current and then you will have some spin accumulation. To give you some idea about how efficient is this effect, usually the term we define is spin Hall angle. It's a ratio of the spin current and the charge current. For platinum, the value is there are a lot of controversies, so it's not easy to measure the spin Hall angle. The values varies from 10 to power minus 2 to 10 to power minus 1 or even far away. To get an idea what does it mean, so if the spin Hall angle is 10 to power minus 2, meaning in 100 electrons only one will be deflected in a way to count for the spin accumulation. And if it's 10 to power minus 3, meaning that in 1000 electron only one will contribute. So it's a very small effect, but it's still detectable. So now if we agree that there is a heavy metal like platinum and then there is a spin accumulation at the edges, now what we want, we put such a metal on top of a magnetic insulator. So when I say magnetic insulator, it means it's a magnet where you cannot pass electric current, meaning it's electrically insulating. So now this stack, we can have actually two situations. So as the platinum metal or any other metal electrode, you only deposit once and then you do not really rotate your current directions because you have once deposited electrode, so you send current and you don't want to redeposit it. But what you can do is you can rotate your magnetization direction, because for magnetization rotation you only need to rotate the magnetic field. So you rotate the magnet around the sample, which will in turn rotate the magnetic field as well as your magnetization of the magnet. There are two situations described here. The alpha angle is up between the current direction, which always stays fixed in this case, and the applied magnetic field direction, which you can change. So if applied field is along the current direction, alpha is 0. In this situation, the spin which will accumulate at the edges of the platinum, let's say at the interface, will be perpendicular to the magnetization. And in this case, you will have a very large spin transfer torque effect where you need to have magnetization perpendicular to the spin polarization direction. Here S is the spin polarization vector. So in this way, a lot of spin will be absorbed, angular momentum will be absorbed. We are talking about the absorption of spin current or angular momentum. It's not about any current flowing into the magnetic insulator. There is nothing flowing inside the magnetic insulator. We are only talking about the spin current or angular momentum. So it will be absorbed when magnetization is perpendicular. However, when it's parallel, there will be no spin transfer torque as they are not 90-degree, they're parallel. This cross product will become 0, and in that situation, the spin current will be reflected back, giving reduced dissipation, so your resistance will be small compared to this. In this way, what I wanted to make a point here is that if you just rotate your magnetic field, you expect to have a dependence of resistance of your normal metal, in this case is platinum, as function of angle of magnetic field. So if you are along the current direction, the resistance is expected to be large, and when you are perpendicular to it, it's expected to be small, giving rise to a cosine square dependence. So this is okay. We have actually, this is the whole point of the spin Hall magnetoresistance. So it's a magnetoresistance effect where the resistance of a top electrode changes when you rotate the magnetization of the bottom magnetic insulator in a periodic fashion. But this theory is not new. It's already known, not only for ferromagnets. Experimentally, it was also observed in ferromagnets as well as in antiferromagnets and many complicated systems. But talking here, you expect to have such a dependence for a collinear magnet. But now a collinear magnet is where magnetization will fully follow or will be aligned with respect to applied magnetic field. But now, if you consider complicated magnets where magnetization is not aligned with respect to applied field, you apply magnetic field like this, but magnetization is still tilted, especially in our system where we have a non-zero Jalushinsky-Mori interaction. So in this situation, you expect to have this curve shifted, as this effect is not dependent on the applied field direction, but it's dependent on the magnetization direction. So you expect to have this curve shifted. How much the magnetization is away from the applied field, you will have an additional phase involved. So whatever I described is, you can see here, is represented with an L, meaning it's a longitudinal SMR effect. You apply current like this, and if you measure resistance also in the same direction, it means a longitudinal SMR. But if you measure like planar Hall effect, meaning you apply you apply current like this, but you measure resistance transverse to it, that is called transverse SMR effect. Here the T represents transverse. You expect to have exactly same physics, especially in this situation. But you will have to consider then the projection of the magnetization, which will be given by mx and y. So you will have again an angular dependence on magnetization, but here you will have sine to alpha and an additional phase phi. this A amplitude is defined by this, which we are going to discuss in a while. But overall, you will see the same effect. It is much easier for us to measure actually the transverse signal than the longitudinal signal, because in transverse you will expect to have less noise. So the results which I'm going to discuss are measured transverse to it, and these equations will be valid. Now I I show you the results. So here is what we have measured. So each point here like this, let's consider this pink curve. Each point here is a complete measurement of angle dependence. So we measure such a curve as function of angle at fixed magnetic field and temperature, and then we fit the data with an equation and get an amplitude as well as a phase. So here we plot the amplitude and here we plot the phase for each full measurement. And all these points are collected in the same way. So to understand what data really represents, I will show you how we combine this data in the color plot. So here only the phase is shown in a color coded plot. How I have shown here is that the x-axis is temperature, the y-axis is field, and the phase values here are shown as a color coded information. So the blue will show 0 phase, and as you go in the other direction, the yellow will show 120 degrees. So now we see what we can understand from this data. This is all experimental data, and these dots represents another measurement, which is only done to understand whether our data makes some sense or not. So indeed, these two measurements agrees very well, because the phase boundaries as well as phase boundaries of these fermions overlap very well. So now I explain only the color coded data, which is from SMR, and not these dots which are obtained from ferromagnetic resonance technique. What you see here is at 51 Kelvin, which is just here. If you are at large fields, you expect to see a zero phase between the applied field direction and the magnetization, because everything will be aligned with the applied field direction. And as you go down, the magnetization will tilt away from the magnetization, and you will expect to have a phase. So that's why the color is changing from blue towards green and then towards yellow, which is actually shown here. So as you are at the large field, there is almost no phase, blue, and as you go downward, this angle starts to increase and then almost 90-degree, or a bit higher in this case. But yes, this is what you see. So it does make sense what we see, and also we could identify this fermion pocket, which is a much more complicated rotation of magnetization. So far, by looking to the data, we could make sense, we could understand, and we could really get everything matched with other measurements, and our phase diagram was fine. But then we wanted to understand what we see. We calculated our data. For that, we considered the energy for which we considered the exchange type energy and Jalushinsky-Maury interaction and Zeeman energy contributions. And we put this energy to LLG equation. We find the minimum and then find the um, magnetization position with respect to the field. So the point here is that the SMR theory tells you that the resistance change due to SMR effect should have only dependence on the MX and Y magnetization projections, and there will be an amplitude. So you will have such a dependence. Here the amplitude, if we talk about this A, You expect to have the largest amplitude when H is equal to Hc2, meaning everything is field polarized. So above 1, you expect to have the large amplitude for SMR signal, and as you go down, you expect to have some certain dependence, but the signal should be largest here and smallest here. However, if we look our data at the measurements which I have shown you, just consider the simple case 51 Kelvin. You can see here that the signals here, here is our Hc2 around 55 millitesla. So you can clearly see that the signals here are much smaller than the signal here. So we are seeing completely different situation what we expect. This was a puzzle which took a lot of time to understand, and Maxime Mossaway and Maria Azhar actually put a lot of effort in trying to understand what's going on. And they introduce a new term which is for non-collinear magnets, especially in our case, which is a gradient term of magnetization. We are not talking about here a dynamic magnetization, but the point here is that if you go along the y direction or along the x direction, you always have magnetization varying in a periodic fashion, represented by this gradient term, which one needs to consider if they want to account for such modulated structures in a magnetic insulator with SMR effect. This gradient term has a field dependence as this change in magnetization is zero when you are in field polarized state, and it becomes most dominant as you go lower in fields. So that's why we have this contribution almost zero at large fields and very large contribution at very low fields. So we can really reproduce this dependence in the amplitude. And with this, we could understand the discrepancy which we have observed in the amplitude of the SMR signal um, before by using just the normal SMR theory for collinear magnets. This was a brief discussion about what we observed and what we expected. Now my question is here, what I wanted to mention is how this effect is relevant if you talk about just normal magnets which have no bulk Jalossian-Skimori interaction. So inversion symmetry is not broken crystallographically. The important point here is that these skyrmions can be stabilized in multi-layers because in layered system at interface you break the inversion symmetry and there is interfacial Jalossian-Skimori interaction. So these twists and these spirals and these skyrmions became relevant. So in this way, whenever you make an interface, you need to consider much more, and this effect which I have described can be very handy to electrically detect some deviation in the magnetization um, at the interface. With this, I would like to conclude my talk. So we have observed SMR effect in non-collinear magnet, and theoretically um, we checked and experimentally, and we observed that we have to introduce a new term to agree between theory and experiment. And one important thing is SMR is surface sensitive, and if there is a twist on the surface sensitive, this chiral twist or edge states, we haven't talked really in this specific talk, but the details can be found here. And it's sensitive to small changes at the interface also. And electrically, you can detect some more complicated textures, and these measurements are rather simple. Understanding may take time, but it's quite a handy technique. With this, I would like to thank everyone for your attention. Thank you very much.